This is Rohini Bawa from Chandigarh Polytechnic College. Today we are going to discuss the digital modulation techniques, from which we are going to discuss the PSK and some other parts of PSK, that is QAM, QPSK, etc. So I'm going to share a screen with you all so that it will be helpful in your further studies and your understanding. So let us start with the modulation of digital data with the help of phase shift key, QAM, bit and baud comparison. Let us start with the PSK. PSK is a phase shift keying. It is a digital modulation technique in which the carrier signal is changed by varying the sine and cosine inputs at a particular time. PSK technique is widely used for wireless LANs, biometric, contactless operations, along with the RFID Bluetooth communications. So in a PSK, it is the another form of analog modulated, where the constant amplitude and fixed frequency will be FC. The frequency is used to show both the symbols, that is 0 and 1, and but the carrier phase of each symbol differs by a phase of 180 degree. The PSK is an M-array digital modulation technique similar to the conventional phase modulation expect with the PSK. The input is a binary digit signal and there are limited number of output phases possible. The input binary information is encoded into groups of bits before the modulating the carrier, so that the phase shift key, the phase of the carrier is varied to represent 1 and 0. Both peak amplitude and frequency remain constant as the phase will be changes. For example, if we start with the phase 0, the degree represents that is 0, binary 0, and then we can change the phase of 180 degree but to sense the binary 1, and the phase signal during the each bit duration is constant and its value depends upon the bits 0 and 1. PSKs of two types depending upon the phases the signal gets shifted, and they are binary phase shift key and quadrature phase shift key. Now starting with the binary phase shift key, this is also called a two-phase PSK or phase reversal key. In this technique, the sine wave carrier takes two phase reversals such as 0 degree and 180 degree. BPSK is basically a double sideband suppressed carrier modulation scheme for message being the digital information. And QPSK, this is the phase shift keying technique in which the sine wave carrier takes four phase reversals such as 0 degree, 90 degree, 180 degree and 270 degree. In this kind of techniques are further extended, the PSK can be done by 8 or 16 values also depending upon the requirement. So starting with the phase shift key, it is a phase of the carrier is varied to represent signal digital data, that is binary 0 and 1. Amplitude and frequency remains constant. If the phase 0 degree to represent 0 and 180 degree to represent 1, that is a 2 PSK. PSK is not susceptible to noise degradation that affects ASK or bandwidth limitations of the FSK. Now 8 PSK, that is in this we can extend by varying the signal by shifts of 45 degrees instead of 90. So with 8 is equal to 2 raised to power 3 different phases. Each phase can represent 3 bits, that is a tri-bit, we can say a tri-bit. In the case of tri-bit, it's for, you just see on your figure, with the figure that is a tri-bit with 3-bit figure. It is a 000, phase will be 0, 001, phase will be 45 degree, 1010 phase will be of 90 degrees, like that. 110 phase will be 270, and 111 phase will be 315. Now starting with the generation of PSK. So generation of PSK, the block diagram is available on your screens, and it consists of a balanced modulator which has the carrier sine wave as the one input and the binary sequence as the other input. Diagram representation is on your screens. So it is generated by using the generation technique of ASK signals. But in the PSK generation, we take the incoming binary data should be in the polar form. The polar form means, here the word arises, the polar form. Polar form means the data should be in two levels, that would be in positive or negative of the amplitude. This is the very simplest form of PSK, where the carrier wave and binary signal in a polar form will be given to the system, and in which the phase represents logic 1 and other phase represents logic 0. As the input digital signal changes the state, this means it may 0 to 1 and 1 to 0. Then the phase of the output carrier shifts between two angles that are separated by 180 degrees. Hence, other names of PPSK are phase reversal keying, and biphase modulation. The modulation BPSK is done by using the valence modulator, which multiplies the two signals and applied at the input. So for a zero binary input, the phase will be 0, and for a high input, the phase reversal will be 1. The diagram representation is shown on your screens. The output sine wave of the modulator wave will be the direct input carrier of the inverted 180-degree phase shifted input carrier, which is the function of data signal. In a BPSK transmitter, valence modulator acts as a phase reversing switch, which depends upon the logic condition of the digital input, where the carrier is transferred to the output either in phase of 180 degrees, out of phase with the reference of carrier oscillator. The valence modulator has two inputs. One is carrier, which is the phase shift, which is in the phase with the reference oscillator, and the other is binary data. For the valence modulator to operate properly, the digital input must be greater than the peak carrier voltage. The BPSK waveform, we can say the power spectral density, a word used here, and for this the power spectral density of a BPSK will be in the shape of the power spectral density, that is the BPSK and ASK signals are similar. Only difference is that the former does not have an impulse at the carrier frequency. According to the bandwidth requirement, the BPSK signal has same, as a BPSK is a non-linear modulation technique. But the BPSK has an advantage over the ASK, that in the sense of performance, BPSK signal is very superior over the ASK signal in the noisy conditions. The relation of BPSK is not susceptible to the noise degradation, and that affects the ASK, now to the bandwidth limitation of the FSK. This means that the smaller variation in the signal can be detected reliably by the receiver. So let us start with the demodulator part. Here, the demodulator consists of the mixer with a local oscillator circuit and a band pass filter, two input detector circuits. The detection of binary shift keying is very much similar to the coherent detection of ASK1, but there are a difference in the choice of threshold level. So it means that both ASK coherent and detector and PPSK coherent detectors suffers from the synchronization like phase and timing problem. According to the block diagram, the BPSK input signal is cleared at the output, and the coherent carrier recovery circuit detects and regenerates a carrier signal that is a both frequency and phase content with the original transmit carrier and balance modulator is a product detector, which the output is the product of two inputs like BPSK signal and a recovered carrier. Again, the filter will be used, and which is used for the separates the recovery of binary data from the complex demodulated signal. BPSK cannot be detected non-coherently because of the fact that the envelope of BPSK signal is the same with the both for both the symbols, that is 1 and 0, and also a single carrier frequency is used for the modulation process. By recovering the band limited message signal with the help of mixer circuit and bandpass filter, the first stage of demodulation gets completed. The baseband signal, which is the band limited, is obtained, and this signal used to degenerate the binary message bit stream. In the next stage of demodulation, the bit clock rate is needed at the detector circuit to produce the original binary signal, message signal. If the bit rate is submultiple of the carrier frequency, then the bit clock regeneration is simplified. Now let us start with the QPSK. It is a quadrature phase shift key. It is a variation of BPSK, and it is also a double sideband suppressed carrier modulation scheme, which sends 2 bits of digital information at a time called dbits, and instead of conversion of digital digital bits into a series of digital stream, it converts them into bit pairs. This decreases the data bit rate of half, which allows space for the other users. And it is an M-array encoding technique. Basically, QPSK is an M-array encoding technique, and in this we can generally observe that the digital modulating techniques studies the available channel bandwidth is not fully used. So the spectral efficiency can be improved upon the sustainably, we can say substantially by using the QPSK. The QPSK is an extension of BPSK1, and in a binary data transmission, the transmission is dependent upon only one or two possible signals during each bit interval. So let us start with the generation of QPSK. So here it is the modulation part. The QPSK modulator uses a bit splitter, two multipliers with a local oscillator, a 2-bit serial to parallel converter, and a summer circuit. So in this, we already know that it is an M-array technique encoding scheme M-array, and where the 4 output phases are possible for a single carrier frequency, because 4 output phases we need. There are 4 output phases, but there must be a 4 different input conditions, because of the digital input to a QPSK modulator is a binary signal, which is the base 2 to produce 4 different input combinations. So 4 different input combinations it is produce 4 different input combinations, and the modulator requires more than a signal more than a single input bit to determine the output condition. With the two bits, there are four possible conditions, that is 00, 10, 00, 01, 10, and 11. We already studied this binary in our digital electronics subject, and the resultant QPSK data are combined into the group of two bits called digits, so that each digit could generate one or the more four possible output phases, that is 45 degree, 0 degree, 135, that is minus 45, and minus 135 degrees. So we can represent by digits in a gray encoded form by transmitting a sinusoidal carrier with all four possible values. So this is our QPSK modulator, and here waveform is shown on your screens with the bits, that is 00, 10, 01, and 11. So let us start with the QPSK demodulator. So QPSK demodulator. So for the QPSK demodulator, here the QPSK demodulator using the two product demodulated circuits with the local oscillator and two bandpass filters, two integrated circuits, and 2-bit parallel to serial converter. The diagram shows on your screens. The two product detectors and the input of demodulator simultaneously demodulate the two BPSK signals. The pair of bits are removed here from the original data. These signals after processing are passed to the parallel to serial converter. So QPSK detection, we use the pair of multiplier, which are followed by the integrators. The multiplier consists of cosine of the carrier and sine of cosine of the carrier. It is already defined in your figure. So cosine of carrier in the upper side and the sine of carrier phase in the lower side. Output integrator is given to the decision making device, which are compared of the sign of two multiplier output and parallel to the serial converter, which interleaves the decision made by both sides. Then finally, it reconstructs the binary data form. It is also able to remove the noise and produces identical to the original one which a QPSK was transmitted, and which QPSK was transmitted, and starting with the relationship. Now starting with the relationship between baud and bandwidth in PSK. So bandwidth similar to ASK and baud, but data rate can be 2 or more times greater. Which is what is the bandwidth for 4 PSK signal transmitting at 2000 TPS? The transmission is in a half duplex mode. For a PSK, baud rate is same as the bandwidth, which means the baud is 5000, but in PSK case, the bit rate is 3 times of the baud rate. So the bit rate will be 15,000 bps. Bandwidth of the signal is 5000 hertz of an 8 PSK signal. Then what are the baud rate and bit rates? We already know that for a PSK, the baud rate is same as the bandwidth, which means the baud rate is 5000. But in 8 PSK, the bit rate is 3 times of the baud rate. We already know that, and it will be 15,000 bps. Now starting with the QAM, that is quadrature amplitude modulation. PSK is limited by the ability of equipment and to distinguish between the small differences and phases, limits the potential data rate. Quadrature amplitude modulation is a combination of ASK and PSK. So the maximum contrast between each signal unit will be bit, dbit, tribit, and so on is achieved. we can say have x variations in a phase or a y variations for the amplitude. X into y is a variable, we are say that these are the variations of amplitude and possible variations, that is QAM and 8 QAM. So in case of QAM, 4 QAM, we are having 0 1 1 0 0 0 1 1 0 and 1 1. On the other hand, for the 8 QAM and the 16 QAM, we are having a 3-bit, that is a tri-bit data, and angles will be 12 phase angles will be provided. Then recommendation that all possibilities are used, not all the possibilities are used to increase the readability of signal. Measurable difference between chips are increased. After that, bit and baud comparison. Here in this bit and baud comparison, let us assume the FSK signal over the voice. And over the voice, we can send great phone lines, can be sent 1200 bps. It requires we can say a 1200 signal units to send 1200 bits, and 1200 bits, and each frequency shift represents bit and baud is 1200. So assuming a k-bit QOM, that the baud rate is only 400 to achieve the same data. So here in the table, you are able to see that there is a modulation technique, units, bit what, baud rate, and bit rate also. So what would be the unit for a 64 QAM? It is hexabit, and the bits and baud will be 6. Baud rate will be bit and baud rate will be n and 6n. So it's like that. Now bit baud comparison. Here let us start with an example. A constellation diagram consists of 8 equally spaced points on a circle. If the bit rate is 4800 bps, what is the baud rate? So the constellation diagram indicates 8 PSK with the points 45 degrees apart. Since 2 raised to power 3 is equal to 8, 3 bits are transmitted with each signal unit. Therefore, the baud rate is 4800 by 3, that is 1600 baud. Now, what will be the bit rate for 1000 baud 16 QAM signal? So in the 16 QAM signal, has we already know that has a 4 bits per unit, since log 2 16 is equal to 4. Thus 1000 into 4, that is a 4000 bps. So let us compute the baud rate for 72,000 bps in a QAM signal. So it has a signal has 6 bits per signal unit, since the log will be log 264, which will be equal to 6, and therefore the 72,000 divided by 6 will be equal to 12,000 baud. If you have any queries, then you can ask me. I hope this topic will be easily understood by you all. Thank you.